6, which is called Kinetic Molecular Theory. From now on, we will be calling it KMT for short. For review, we're going to watch this egg in a flask video and then draw a before and after picture and then find the final pressure in this flask. So what's happening in this video is he's lighting a piece of paper and he's throwing it into the flask. This is going to simulate the temperature rise. Okay? So as the temperature rises, we place the egg on top, and then the flask begins to cool and approach room temperature. So as it cools, we notice that that egg begins to get sucked in to the flask, decreasing the volume of the gas inside. We're going to see what final pressure inside this flask. Let's begin by drawing final and initial conditions for this video. So initially what he did is in the flask, he heated it. Oh, that's a horrible flask. So adjust that a little bit. Perfect. Okay, and we'll label it flask so nobody's confused with my drawing. And then we have an egg placed on top. Egg. And we say that the initial volume, or where the seal is forming on the flask, gives the gas inside about a 250 milliliter volume. Okay, so we're going to trap the moles of gas. So the moles of gas is going to stay constant with this. Final conditions, what we're going to do is we begin to see the egg get sucked into the flask. So again, let's label the flask an egg so nobody questions what I drew. And that decreases the volume of the flask. So now that gas inside, similar moles, we're going to say 3 for now, has smaller area inside. So from here, let's kind of come up with some numbers to calculate the final pressure. So initial pressure is standard ambient pressure. So P1 is equal to 100 kilopascals. V1 is 250 milliliters. T1, we're going to assume that it got up to 100 degrees, okay, water boiling temperature. Convert that into Kelvin. Okay, and so this will give us 373 Kelvin. We are looking for P2. V2 is 150 milliliters, and we're going to assume that the temperature reaches standard ambient temperature, which is 25 degrees Celsius plus 273.15, which is 298.15 Kelvin. Okay, so now let's use the combined gas law formula and isolate for P2. We'll leave our conditions up there. P1, V1, T2 is equal to P2, T1. This is of interest to us, so we are going to divide both sides by V2. V2, T1. On this side, V1 cancels, V2 cancels. And we are left with P2 is equal to P1, V1, T2 over V2, T1. After we plug in our numbers, P1 is 100 kilopascals, V1 is 250 milliliters, and then we need T2. So this is where common mistakes are made. People usually plug in T1 here, so make sure you are plugging in the appropriate temperature. Divide by V2, which is 150 milliliters. Make that look like 5. And T1, which is 373.15 Kelvin. Kelvin cancels out with each other, milliliters cancels out with each other, and you are left with kilopascals, which is great because we are looking for pressure. Once you plug that into your calculator, you should get a rounded answer of, we get a final pressure of 133 kilopascals. All right, let's jump into today's lesson. So we're going to be describing the properties of KMT, ideal gas, and use and apply ideal gas laws. and know the ideal gas constant. Kinetic molecular theory, or KMT, states that entities are in constant motion and they collide with each other. So basically, an entity, if you don't know what that word means, is a particle, a molecule, basically anything small that can crash into each other. So we're going to be using our textbook to fill in this page. So, I'll just help you guys with this. So, an ideal gas law, the first point is that for a gas to behave ideally or perfectly, molecules are far apart. Okay, so if we were to draw a diagram of that, molecules have distance between them. They are free spirits. Going on to that, the second point is molecules move freely. So they go in all different directions and occasionally collide with each other. Okay, so again, we're going to refer to that depiction there. Lastly, molecules, when they collide with each other, have elastic collisions. So what that looks like is you have two molecules that are coming together, and then they collide with each other, and then they go on their way. So when they collide with each other, they don't squish necessarily, they kind of just bounce off each other and then go back in opposite directions. Okay, so this is how an ideal gas behaves. However, we are going to come into the circumstance where we deal with real gases. These are how gases are in our day-to-day life. They're real. So what happens is, under high pressure, a gas can no longer move. So it has very limited movement. This is a problem because for it to behave ideally, molecules like to move freely. So what happens is if you put molecules under really, really high pressure, they're going to be squished together and they can no longer move. So they do not like that. So they don't behave ideally anymore. The next thing is low temperature. So if the temperature gets too low, a gas will turn into either a liquid or a solid. So same thing, it's limited movement. May turn into a liquid or a solid. So what happens is when the molecules come to collide with each other, they're actually going to stick together. When they stick together, they're going to turn into a liquid or a solid. Remember, when molecules stick together, they will change state because the temperature is so low. The last thing is there's inelastic collisions. So when they come together, that kind of explains why they turn into a liquid or a solid. Right here, when they bounce off each other, they're going to separate. They bounce off of each other. Here, in an inelastic collision, what happens is when they come together, they really squish up on each other. And when they squish, there's a possibility that they won't separate. And that's how they can turn into a liquid. So a little bit of an additional information about elastic collisions here. So when this elastic collision happens, kinetic energy is conserved. Therefore, if kinetic energy is conserved, Therefore, temperature remains constant. In an inelastic collision, it's opposite. Well, kinetic energy is not conserved. Therefore, temperature experiences a change. And that change is usually a decrease, which will turn the state into a liquid or a solid. All right, so an ideal gas is kind of like a perfect gas. So it perfectly, that's not how you spell perfectly. Perfectly obeys all gas laws. So what we just listed on that past screen, they have free movement, they have space between each other, they have elastic collisions. So we're assuming that the gases around us are doing that. However, like it is to find perfectness in our world, gases are also not going to be perfect. So however, this theory is hypothetical. It's a big assumption we are making to make our lives easier when we do these calculations. So a real gas deviates. Deviate means that it doesn't follow the rules, okay? It follows away from the trend that we expect. It deviates when we have it deviates from gas law under certain conditions, okay? Here are the certain conditions. Extremely high pressure. Like we said, if those guys are extremely stuck together, they can no longer move. If we have low temperature, again, if we have low temperature, those gas particles are more likely to become solid or liquid. And if we have densely packed molecules, so this again, the molecules are very close to each other. So think about riding Calgary Transit during rush hour. You are a densely packed molecule. So if we were to go into a lab and we were getting data and we were looking at an ideal gas law, they would form a straight line. Try that again. Straight line. However, if we were going into a lab, we would most likely witness a real gas. And they would not form straight lines. I'm going to show you kind of what that data would look like. Let's look at some ideal gases. Let's take a look at Charles' law. Charles' law, the data looks clean. We see that those points are making a very straight line. Okay, we'll say that we're manipulating our temperature and our responding is volume. Makes a very straight line. That's Charles' law. Let's label it. What about Boyle's law? Let's say we have pressure as our manipulated, volume as a responding. We start plotting the points, and we get this nice curve. So let's look at real gases. No. Let's do Charles again. So we notice that we'll keep our variables the same. Temperature is manipulated, volume is responding. And we get data points that kind of look like that. So from here, let's draw a line of best fit. So notice how the line is not going through all of the data points. We see that that one didn't make it, this one didn't make it. This is what I mean by deviation away from the trend. So we see the general trend, that the relationship is proportional, but all of our data isn't necessarily going to land on our curve. Same thing with Boyle's law. real gas, they were manipulated pressure, and our responding is volume. Again, we start getting our data points. We notice that there are points deviating from the line. Okay, so this is what more accurate data would look like in a lab versus the ideal. So remember that oils, Charles, the S should go there, turn that into a comma. Charles combined Lucia and the ideal gas laws. And the ideal gas law formulas are all created for ideal gases. So gases that behave perfectly. However, in real life, the gases around us are not perfect. Like a lot of things in our life, nothing's perfect. Therefore, when using these gas laws, we are making a very big assumption. And considering that the gases are around us are behaving ideally. Okay? So the general thing that I'm trying to say here is all these formulas that we're going to learn in this unit, have learned, they are based on the gases around us behaving ideally. However, the gases around us are not ideal, they are real, so it is a big assumption that we are making when we do these calculations. Okay, so we're going to talk about the ideal gas law. The formula is PV is equal to nRT, or as I learned it in high school, the Perv-Nert law, where R is a constant, okay? So now we're going to be manipulating all four of those variables that I introduced to you. R is now going to be our new constant. And the value for R is 8.314 kilopascals times by liters over mole Kelvin, or for short, kPal over mole. So you have to be careful now about the units we use. We have to use units that are specific to the R constant. So from now on, whenever you're using ideal gas law, pressure needs to be measured in kilopascals. Moles and mass, remember if you have mass, you're able to get moles, need to be measured in moles. Volume has to be in liters, and temperature must be in Kelvin. This is so that we can accordingly cancel out the units when using this constant. Okay, let's do an example of using the ideal gas law. Right off the bat, we know that when you're using ideal gas law, there are no longer any initial or final conditions in these problems. Okay, so what is the volume of 3.35 moles, that's going to represent N, of neon at 42.5 degrees Celsius and 96.5 kilopascals. Okay, so P, V, N, R, T. P is 96.5 kPa. V is what we are looking for. N is 3.35 moles. And T is 42.5 plus 273.5, which gives me a temperature of 315.65 Kelvin. R is 8.314 kPa over mole. Yeah. Okay, so we're going to use the formula. PV is equal to nRT. We are looking for V, so I divide both sides by P. P cancels out. V is equal to nRT over P. Let's sub values in. N, 3.35 moles. And then we have R, 8.314 kcal over mole. Now, and T, which is 315.65 Kelvin over pressure, which is 96.5 kilopascals. Okay, so let's do some unit canceling out. Mole cancels out with mole. Notice how this mole is in the denominator and this mole is in the numerator, so they cancel each other out. Every numerator cancels one denominator out. Kilopascal cancels out with kilopascals. Kelvin cancels out with Kelvin. If this unit stuff confuses you, make sure that you have the correct units for your pressure, your volume, your moles, and your temperature. You don't have to put the units into the calculation. But they need to be matched, otherwise your calculations will be wrong. So you cannot use atmospheres or millimeters of mercury when you're calculating using the ideal gas-law constant. When you plug that in, you should get an answer of, we get a volume of 91. We have 3 significant digits, so 91.1 liters. Here is an example for you to try on your own. I'll write the answer for you, and then you can check if you did this one. Okay, once you plug this in, you should get an answer to 2 significant digits of 27. Okay, since we're looking for chemical amount, 27 moles. Okay, so now what we're going to do is use mass. So remember, when you have mass, you can get moles. So if you're going from grams to moles, you will use molar mass. Okay, so it's asking us what the temperature, so we're looking for T, of 6.5 grams of sulfur dioxide that occupies 10 liters, that's V, at a pressure of 125 kilopascals. Okay, so like I said, when you have mass, you have moles. So let's convert that. Actually, let's list our variables. P is equal to 125 kilopascals. Volume is 10 liters. N is 6.5 grams. So we're going to convert this into moles using molar mass. The molar mass of sulfur dioxide is 64.07 grams per mole. So we're going to do unit analysis here. You're going to divide by 64.07 grams and multiply by the moles. Grams cancels out, and you are left with moles. Okay, let's plug that in. You get 0.10145 ... mole. This is an intermediate calculation, therefore you will not round. Okay, and R we know is 8.314 kcal per mole. And T is what we are looking for. We'll give our answer in Kelvin. Okay, let's use our formula. P V is equal to nRT. We are looking for T. Divide both sides by nR. N cancels with N, R cancels with R. T is equal to PV over nR. Let's plug these values in. 125 kPa multiplied by 10 liters divided by our moles. I'm just going to write a couple significant digits here, but just know when you are plugging it into your calculator, you want to grab the full answer. And then 8.314 kcal over mole. Okay, mole is in the numerator in the bottom here, cancels out with this one. Liter cancels out with liter. kPa cancels out with kPa. This temperature, this Kelvin, is in the denominator twice, which makes it come up into the numerator. So your answer will be in Kelvin. Let's calculate that out. We get an answer of 1481 Kelvin. We're allowed to have 3 significant digits, so we will put this into scientific notation. 1.48 times 10 to the 123 Kelvin. Okay, one more example, and then you guys will try one on your own. What is the mass of oxygen gas sample in a 29.0 liter container under 243 kilopascals of pressure held at 43 degrees Celsius? Okay, so we're looking for mass, which means we first need to link and find number of moles. Because again, if you have mass, you have moles, and you can go back and forth. This is volume, this is pressure, and we have T. Let's list out our variables. P is equal to 243 kPa. V is equal to 29 liters. N is our unknown. It will get us to mass. R is our constant, 8.314 kcal over mole. And T, lastly, is 43 degrees Celsius, which we will need to convert into Kelvin, which gives me 316.15 Kelvin. Okay, we use our ideal gas law now. PV is equal to nRT. We are looking for, not that guy, we are looking for N. So I'm going to divide both sides by R and T. R cancels out, T cancels out. N is equal to PV over RT. Let's plug in our values. 243. Let's put units. Kilopascals times by volume, 29 liters, divided by R, which is 8.314 kcal over mole. Multiplied by 316.15. Let's cancel our units. kPa cancels out with kPa. Liter cancels out with liter. Kelvin cancels out with Kelvin, leaving mole in a double denominator. Double denominator means that it pops up into the numerator. All right, so we get an answer of 2.681 mole. Again, this is a mid calculation, so we're not going to round yet. So imagine that dot, dot, dot. Our goal is to find mass. Like I said, you need to read what the problem is actually asking you to do. So we're going to take our mole. 2.681 mole. I'm just writing that many significant digits, but you should be grabbing the full answer. And we're going to turn this into grams. And the way that we do that is find the molar mass. O2, oxygen gas, has a molar mass of 36 grams per mole. So we're going to use this to convert our moles into grams. 36 grams over mole. Mole cancels out, and we are left with 97 grams of oxygen. Here is an example that I want you to try on your own. You are looking for temperature in Kelvin. So at what temperature does 16.3 grams of nitrogen gas, this is important because you will use it to calculate molar mass, have a pressure of 126.7 kPa in 25 liter tank. Okay, I'm going to give you a moment to calculate this out, and then you should get an answer of 655 Kelvin. If you want to practice converting into Celsius, you get an answer of 418.3 Celsius. Because it's asking for temperature in Kelvin, this is what I'm looking